Set your hand on a table and it feels like the simplest kind of contact. Solid against solid. Skin against wood. Physics gives that moment a stranger shape. At the scale of atoms, your hand does not touch the table the way common sense suggests. In this video, we follow that ordinary moment all the way down, from the feeling in your skin to the electrons at the surface, and then to the quantum rule that helps give matter its shape. First, a correction. This does not mean touch is fake. When you rest your hand on the table, something physical happens. The skin bends a little. The tissue underneath compresses. Tiny receptors in your skin respond to that pressure and send signals into your nervous system. You experience touch when your brain reads force and deformation. The feeling is real. The deeper question is what creates that force before any tiny hard surfaces could ever meet in the picture most of us carry around in our heads. To answer that, we have to shrink the scene. You have probably heard that atoms are mostly empty space. That is true in one limited sense. The nucleus is tiny, and the electron cloud spreads across a much larger region. That phrase can still mislead you. It makes atoms sound like little solar systems with room between hard parts. They are not. The electrons that mark an atom's outer reach are not tiny beads on neat orbits. They form a spread-out quantum cloud, a region where the atom can interact with the world. Matter is sparse in that sense, but not empty in any everyday sense. A surface is not a row of microscopic marbles. It is closer to the outer territory of many electron clouds packed together. Now bring the hand back toward the table. Long before any nucleus comes close to another nucleus, the outer electrons in each material start to matter. Electrons carry negative charge. Nuclei carry positive charge. As the two surfaces approach, those charges interact across the gap. This is the first layer of what we call contact. Your hand is not waiting to hit a tiny hard wall. It is entering a zone where electromagnetic forces rise very quickly. That growing resistance pushes back on your skin pushes back on the table, and your nervous system reads the result as touch. At this point, you could say negative charges repel so matter feels solid. That is part of the story. It does not reach the bottom of it. We would still be missing something essential about why atoms have layered structure, why electrons settle into orderly patterns, and why squeezed matter becomes so resistant. Charge repulsion helps shape the boundary. It does not explain the full architecture on its own. Underneath it is a stricter rule. Identical electrons cannot share the same quantum state. Once that rule enters the picture, the surface of a table stops looking like only an electric boundary, starts to look like a quantum one. The deeper rule is the Pauli exclusion principle. In plain language, identical electrons cannot occupy the same quantum state. They cannot be exact duplicates in the same physical arrangement, with the same quantum description. So electrons do not all drop into one lowest slot like marbles in a bowl. They spread across different allowed states. That sounds abstract, but it is one of the basic reasons matter has structure at all. Now for a key distinction. Pauli exclusion is not a hidden force, and it does not mean electrostatic repulsion under a different name. It is a rule about which electron arrangements nature allows. When you push two pieces of matter very close together, that rule starts to matter. More overlap leaves fewer easy arrangements available. Some electrons have to move into higher energy states. That makes compression expensive in energy very quickly. In practice, you feel that rising energy cost is strong resistance. So the surface under your hand is not a wall of tiny hard beads. It is closer to a steep no-entry zone, shaped by electromagnetism and made steeper by this quantum no-sharing rule. This is not some special effect that appears only when you press on a table. The same principle already works inside every atom. Electrons gather around a nucleus, but they cannot all collapse into the single lowest state. Pauli exclusion forces them to fill the available states in order. That is why atoms develop shells and layers. It is why different elements have different sizes, different outer electrons, and different chemical personalities. If every electron could share the same lowest arrangement, atoms as we know them would not exist. The periodic table would lose its pattern. chemistry would lose much of its structure. So when you talk about the world feeling solid, you are seeing the surface result of a deeper architecture. Matter has volume because its electrons have to organize, not simply collect. Scale that up from one atom to trillions and you get the behavior of solids. In metals, semiconductors, and other materials, electrons do not occupy energy states at random. They fill them under the same Fermion rules. That filling helps determine whether a material conducts, resists, bonds, bends, or holds a crystal shape. So exclusion is not just a line in a textbook. You can measure its effects. In some ultra-cold atom experiments, physicists have seen patterns that come from this no-sharing rule alone. Neutral fermions, with very little ordinary pushing between them, still settle into spacing and order because identical particles cannot all occupy the same state. The principle itself is invisible. Its consequences are built into the structure of materials all around you. Now the scale widens, but the idea stays the same. When a star like the Sun runs out of fuel, it can end as a white dwarf, a hot, dense stellar remnant about the size of Earth, but with a mass comparable to the Sun. Gravity tries to crush it further. The electrons inside cannot all be pushed into the same low-energy states, so the matter resists compression. The result is electron degeneracy pressure, one of the great large-scale consequences of the Pauli exclusion principle. The same rule appears here under far more extreme conditions. That is the quiet surprise at the center of the story. A tabletop does not resist your hand in exactly the same way a white dwarf resists gravity, but both belong to the same family of physics: electrons, allowed states, and the rising cost of compression. So the old line that you never really touch anything needs a careful translation. Touch is real as force and as sensation, but it is not tiny hard surfaces meeting the way common intuition imagines. Matter meets matter through fields and quantum rules. Rest your hand on a table, and the same kind of rule that helps give that surface its firmness also helps hold up a dead star. This is where the idea widens. The same exclusion rule that keeps ordinary matter from compressing too far also becomes decisive inside a white dwarf. After a star like the Sun runs out of fuel, gravity drives its remains inward with enormous force. The nuclei pack tightly, electrons are forced into fewer available states, and Pauli exclusion makes that crowding more costly. What pushes back is electron degeneracy pressure, the large-scale result of the rule that identical electrons cannot all share the same quantum state. In a white dwarf, that pressure can support an object with roughly the mass of the Sun, compressed to about the size of Earth. So the physics under your hand is part of the same deep structure that helps dead stars resist collapse. A tabletop and a white dwarf could not be more different, but both are shaped, in part, by the same quiet quantum refusal to let matter pack without limit. So, have you touched anything? Yes, in the sense that matters to your body and your experience. Touch is real. It is not tiny hard surfaces meeting the way common intuition suggests. It is force, resistance, and sensation at the boundary between atoms, shaped by electromagnetism, and by quantum rules that do not let matter overlap without cost. Physics does not make the world less solid. It tells you what that solidity is. And once you know that, even a hand resting on a table feels a little larger than it did before. If you want more of these quiet journeys into how the universe works, you can subscribe.